some of the recent methodology on what embedding. Professor Bishwanath, is it correct?
Yeah, that is true. Yes.
So, so I just to make this presentation a bit different, because so if you talk about the methodologies of this recent word embedding, the content is going to be almost the same. So just to make this talk a little different from say what in the first session you might have already exposed to. So I'm going to discuss a bit some backwards. Okay, how what are the say earlier form of word embedding, and say what are the differences between earlier methods and the new methods. Okay, so that is how I have planned today's talk. Okay, so just to begin with, so I think next few slides will be almost familiar with you, and when it as you know that what embedding is primarily for text analysis. So text analysis include various applications like say document classification, sentiment analysis, NER. Okay, then similarity between document words and so on, right? So when it talks about, so these are the various text analysis applications, and this is not exhaustive. And this I only just to give a kind of feel. I have just listed a few of them, like say some text recommendation or search engine, text classification, sentiment analysis, head or communal speech detection, fake news detection in NLP, part of speech, NER, machine translation, machine transliterations, video or audio tagging, and so on. Okay. So you take off any say text analysis problem and the machine learning application. So maybe that they will fall in either in the classification problem or clustering problem, right? So when we talk about classification and clustering, so what are the basic requirements? Okay. So first we have to know how to represent the words or the sentence or the document, okay, depending on the nature of the application that you are going to look at, or the nature of the task that you are going to solve, right? So just to take an example, say given a text corpus, if I want to find something like semantically similar words together. Semantically similar words means if I give a word something like good, then maybe some similar, say semantically similar word might be nice or bad, and so on, right? So how do I find such similarity? Okay. Or say if I talk about something like document classification, given a text document, whether it belongs to some class like entertainment domain or sports or movie and something like that, right? So how do I do that, right? Or say if I given a tweet post, if you want to check what is the underlying sentiment present in that, is it a positive sentiment or negative sentiment, how do I do that? So for performing any of these machine learning or say any similarity based methods, or say some feature based machine learning methods, first requirement is to have some of the effective representation mechanism, right? So if you have a very good representation, your model will always be performing well. So so representation is one of the core area in any machine learning or data mining area, right? So whatever the say efficient learning model that you have, but if your representation is not good, then you will not get a good performance. But if your representation is good, then even with the very naive approach, you may be able to get very effective performance. So I So representation is the most fundamental area in any of these machine learning domain, irrespective of whether it is NLP or some image-based or some other video-based, whatever. So, so in the word embedding, what we're going to talk about is finding such effective representation. Okay. So, what do I mean by some say effective representations? Just to give a notion of this, so I'm just trying to give the show this figure. So let us assume that the dots in these figures are words, okay, and we have projected this in the two-dimensional space. And after say this projection, if you find it say similar words, okay, words having similar semantics, they lie together. So in this figure, if you see all the green say points that relates to body parts are lying together, all the words related to food lying together, words related to city lying together, and so on. So if these related words are lying together, then this is a good representation. Okay? Then if you have a good representation, any learning models, classification, clustering will always be performing well. Okay? So what embedding is about, how to generate such effective representations for say for different machine learning tasks. Okay. So now just to before going to what embedding, let us see how say different how this journey starts. Okay. So before this embedding concept, okay, so the way we started exploring the text analysis and the way we represent the corpus is in the form of the metrics that I'm showing in the left hand side. So what is this matrix? This matrix is nothing but document and term matrix. That means in the row I have the documents, and in the columns I have the terms. Let us say these terms are nothing but the unique words, the set of unique words present in your corpus. Let us say you have m number of unique words in the corpus, and every document, and D1, D2, D3 are the list of documents, and you have n number of documents. Okay? So I can create a matrix, document and term matrix of the order n by m, where n is the number of documents in the corpus, and m is the number of unique words in the corpus. So the moment I consider this, I can create a matrix, something like if a term is present in a particular document, then you give 1. If it is absent, you give 0. Like say T1 and D1, it is 1. That means the term T1, the word T1 is present in the document D1, but the term T2 is absent in the document D1, and so on. Okay. So likewise, I can use absent and the present and create a matrix, and this matrix represent my text corpus. Okay. So this particular representation is something like Boolean representations. So instead of Boolean representation, you can also use some other weights like say term frequency, TF, IDF, or any other weighting measures like BM25 and so on. Okay. So that might be a weighted matrix. Okay. So now, the moment I have this matrix, then you can see that each row, what is this row? Row is nothing but the is a vector, right? And the elements of this vector corresponds to each of the unique words in the corpus. So these unique words are the features. So that basically means the documents are represented by a vector. So once I have this, once I represent this document in the form of a vector, then if I want to ask questions like, given a document D1, what are the other similar document to D1? Then maybe you can perform some vector similarity methods like cosine similarity, or say Euclidean distance and so on, any distance measure or similarity based method you can apply on the vector. Okay, that is the advantage. Similarly, each column here, you can also see this as a vector, right? And the features defining the terms are nothing but the documents. So terms are defined by a vector, with the document as the features, and the documents are defined by the terms as the features. So this matrix itself give me the vector representation. Okay, and likewise, if I ask the question like what are the similar terms to the term T1, I can apply these vector similarity methods to find a similar methods and so on. Okay. So in this representation itself, if I want to build some classifier, document classifier, for example, classify a document to some movie or say sports and so on. So since I have this representation in the vector space model, so I can directly apply classifiers. I can also build clustering models. I can also perform this similarity. So whatever the task that I need, right, in the NLP, I can work in this space as well. Okay, so whether in the document space or in the term space, right? So this representation is quite fine, so you can solve. Okay. But the question is this representation a good representation? So because what we are looking is for an effective representation, right? So this representation might not be an effective representation. So why it is may not be an effective representation? One of the problems, especially in the text domain, is the number of features. Say, for example, documents are represented by terms, number of features, this number of terms M. Okay, it is going to be huge. And if you're working in the text domain, you may be aware that, say, for about 10,000 documents of reasonable size, you may be having tens of thousands of unique words, right? So the number of features set is going to be very, very large. And 10,000 is a small number, so your collection is going to be in terms of millions for a reasonable NLP problem, text mining problem. So for a million, say, document, your number of features are going to be a few thousand, say hundreds of thousands, right? And I just missed one point to inform. So these terms, so what are these terms? It may be, so I was telling that these are unique words. So if I consider unique word, this is something like unigram. So if you extend to bigram, trigram, and so on, the number of features are going to be even much, much larger. Okay? So problem with this representation is the feature set is going to be extremely large, and many of these features are not going to be useful. Many of them will not be useful. So that is another problem. Again, if your data collection is not very, very large, is not huge, then this representation is going to be very sparse. Just imagine a document where you may have about 100, different unique words, and your total feature space is something like million. Then this matrix is going to be extremely sparse, right? So sparsity is again another problem. Again, another problem is you might have heard about curse of dimensionality. As you increase the features size, your performance may start dropping, okay, because of the sparsity and others. So these are the basic issues of this form of representation. So I can use this representation, but this is not a good representation. So then what people have done, that is what embedding is about. Okay? So what embedding is, so you may have different form definitions. You may have found, different definition in different literatures. But just to give a high-level notions. I'm just referring as what embedding is a dense representation of words in the form of numeric vectors in low-dimensional space. So that basically means this high-dimensional space, this vector representations, I'm going to transform into, say, low-dimensional space. So this is like a dimension reduction, if you basically see. Right? If you are, say, from high dimensional space, you are reducing to low dimensional space without losing information. Okay. And how do you actually reduce the number of features? So if you have done in machine learning, so you may have two ways of reducing the reducing the number of features. One is something like feature selection, where you only select good features and others you ignore. That means you are throwing away some of the information. That is the feature selection. And another is like dimension reduction, where I do not ignore the features, but instead I transform from high dimensional space to the low dimensional space. Okay, so here we are talking about, say, projecting from high dimensional space to the low dimensional space, and that will generate, say, dense representation. At the same time, the underlying method that you are going to use will also try to capture something like semantic relation between the words in the documents and so on. Okay? So that is for the what embedding. Okay? So if you look at the different methods people have used for what embedding, so the term embedding is very recent, but the problem is very old. This is a very, very old problem, and people have been working, say, to find solution to this. And in the past also you have got many effective methods. So some of the very commonly used method for generating this word embedding, though the term embedding was never used earlier, before this word to back and so on. So, but the underlying motivation and idea still remains same. Okay? So some of the earlier method, if you see, they can be principal component analysis. So if you know, exposed to machine learning, you may have heard about it. Then singular value decomposition or latent semantic indexing, some topic modeling like latent allocation and so on. So these are some of the earlier methods that have been used for generating the embedding or generating the representation of the words, representation of the documents and so on, and they are found to be very, very effective as well, in spite of the limitations. Okay, so but so this, if you look at the PCA and the singular value decompositions, they are like something like a matrix factorization based methods, so linear algebra that is being applied. But they are not the neural models. But in the recent time, people have come up with neural models like word to back, then say a variation of it, glove, fast text, bird, and so on. So these are the recent say word embedding methods. Maybe I started with word to back, and then many people started working on it and proposed many variants of it and so on. Okay. So what I'm going to do is I'm going to go back to this principal component analysis and singular value decompositions, and give a notion of how to generate embedding of, word embedding using PC and SVD, and then briefly on word to back. I hope you have already seen that presentations in the first sessions. Okay, then that I will just talk about how to apply this and the embedding that you get from these methods for various NLP tasks. So I will with this I will go to PCA. So PCA is okay, nothing but principal component analysis, and this is one of the method for dimension reductions. So it's nothing but generating embedding from what embedding using PCA is nothing but in your corpus, that term and document matrix, you apply PCA, okay, and that is what the embedding that you're going to get. So what is PCA? PCA is one of the dimension reduction methods. Okay. So just to give a basic understanding of PCA, let me start with a very one example. Let us assume that I have data sets. So this data set is something like a vehicle data set. I have 6 vehicles, and each vehicle is defined by 4 features like height, weight, number of wheels, CC, and so on. So you see that, okay, each vehicle is defined by a vector of dimension 4. Okay, so now what I'm trying to say is that if I want to visualize say this data, and if we assume that I have only one features, let us say I have only height, then I can visualize this these samples using a line projection on a line. So this line, blue line, is the line representing the height, and the cross that you have on these lines are the respective points that you get from this column. So 6, 5.5, and so on. Okay. Each cross represents each of the samples. So if it is one dimension, this is how I can see, right? So if I have 2 dimensions, if I have to say 2 dimension, 2 number of features, then I can visualize in the plane, XY plane. So each rectangular boxes are the samples in this XY plane. Likewise, I can up to 3 dimension, like height, weight, wheels, I can visualize in the 3 dimensional space. But from say beyond 3 dimensional space, I cannot visualize anymore, right? So in one way, dimension reduction can also be used for visualization. Say huge dimensional space, you reduce to say 2 dimension or 3 dimensions and try to visualize it. So so for beyond 3 features, I cannot visualize, right? So now for simplicity, let us discuss 2 dimensional space. So I have XY plane, that is nothing but height and width, height in the x-axis and width in the y-axis. And let us say these points are the point in this XY, and these rectangular points are the points in this XY space. Okay. So now this is my data set. So in the rectangular box in the right-hand side, this is my data set. So now my question is, if I want to represent this data set using x-axis, like the height is a vector, right? This x-axis, if I want to represent by x-axis, what do you mean by that, right? So that is nothing but take a projection on this x-axis. So these data points, you take the projections, okay? And whatever is the projected points, they are the representations, okay? So what is this projection? So if you see this height, the x-axis is nothing but a vector that is 0, 1, and a 0, right? If it is a unit vector, this is going to be 1 and 0. So these projected points are nothing but the product between the dataset D and the vector, the x-axis 1, 0. So that will represent you the represent the project this data representation of this data set by the x-axis. So this can be something that you can easily see. So if you multiply each sample in the data set by x-axis, that is nothing but d into x, you are getting 6, 5.5, and so on, right? So this is what the projection on the y-axis, x-axis. The same thing if you do on the say y-axis. So that is nothing but you multiply this data set with the y-axis, that is nothing but 0, 1 unit vector, then you will get the projection, right? So that is nothing but all the cross point in the vertical line, this with axis. So this is the projection. So this means that if I want to do a projection of these points on any random vector v, okay, what I need to do, I just need to multiply this data set by this unit vector of this v, right? That's it. So that is the projection of these data points by this x. So this projection basically means I am representing this data set by this vector. Okay? So that is what the projection. So why I'm explaining this is exactly what you are going to do in the PCA. So now, just to give some more information, let us say on this vector v, if I'm doing projection of some random point x, okay, this is my projection. And if you try to construct these rectangles, say, and the size of this rectangular sides are something like a, b, c, then you know that c square is equal to a square plus b square. And if this vector v, if you move closer to the point, then you will observe that a is larger than b, right? And if you move further from x, you will see that b is larger than a. That means what? A and the b are inversely proportional. So as b increases, b will decrease. Likewise, if b increases, a will decrease. Okay, so a and b are inversely proportional. These are some of the requirements in the PCA. That's why I'm just mentioning this. Then similarly, so whole idea is something like I have these points in this two-dimensional space, and I want to find a line, a vector that probably fits the best in this, say in these data points. Then that means I will take a vector and take the projection. Okay. So since the line is not passing through all the points, there are some errors. So this length of the projection that you have from each of the points, they are the they are the error. Okay, so this for the one data point one, you have this red projection. This is the error. Likewise, total error for this projection is sum of all this vertical length. Okay, so this projection length, this is the sum of the error. So you may have infinite number of lines around these data points. Okay, among those points, you need to find the particular line that has the minimum error. Okay? That is nothing but the best fit. That is what we are looking at in PCA. Okay, so for some mathematical simplicity, and we are going to do project we are going to do some adjustment on this data points. So so first what we're going to do is I will try to find say sample min. Sample min is nothing but find the min of the x-axis and min on the y-axis, and get the sample min, and do the say shifting min. That means you bring your data points in such a way that your sample min become the origin. That basically means I want to do the analysis of the projection around the min point. Okay, and so so from min, how the projection are distributed. Okay, that is what I want to do. That's why I'm bringing the data point say towards the min. This is like min shift. Okay, min shift means you are shifting all the data points towards the sample mins. Okay, origin will be brought to the sample min. So this is the first step in PCA. So given a data set, you have to perform min shift. Okay. So what do you mean by min shift? Min shift is nothing but min adjusted. So whatever your say original data or original value, you subtract the min points. Okay. So h minus m, and like m, where m is the min, sample min, and w minus m, and so on. So the value that you have here, earlier it was something like 500 and so on. Now it is something like 1.2 and 125 and so on. This is the now min shift, say min adjusted data points, data set of your original data sets, and do the say same plot weight and the height. Now you see the origin passes to the min. Okay, so now on this min shifted data set, you try to find the best fit line, the vector with the that fits the best. That is what I am going to do. We are going to do. So, like say, let us say V is one of the such vector, and what is the error with that? Okay, so if you see P1 is the this projection distance for the sample 1, P2 is the projection distance for sample 2, and so on. Sum of all these samples, this projection error, this is nothing but the sum of the error. Okay, but some of the projections are positive on the positive side direction, and some are on the negative directions. So if you perform some of these, your say error is so positive negative will cancel out, and that is what we don't want. So instead of that, we are going to do something like sum of the square error. Okay, so you perform square of these errors and perform sum. Okay, this is what we are looking at, and I'm looking for such a vector that has the minimum this sum of the sum of square error. That is what the best fit line. Okay, so that is what we are looking at. So if you remember the relation between x and the a and the b, so instead of p, say projection distance, I can if I do distance of the projected point from the origin, that is nothing but d. So d1, d2, d3, and so on. So it is same. So earlier you're looking for minimum project errors. Now that is equivalent to finding maximum sum of this distance. Okay. So this sum distance I can have again. Likewise, it can be positive, negative, because it can lie say in the left other side of the origin and so on. So to avoid that, we are going to do sum of square distance. Okay. So now base fit is something like maximum, the particular vector with maximum square distance. That is what we are looking at. Okay. So let us assume that you have found such a base vector. Okay, and that vector is what we call as the first or principal component. Okay, this is the first principal component. That is what we are looking at. So principal component analysis, okay, what we're looking is those principal components, right? So this particular vector with the maximum sum of square distance, this is the say first principal component. Okay? In other words, we will see that this is also equivalent to eigenvector of some covariance that we'll say look at after later on. Okay, so this is the component that we are looking at. And this sum of square distance is like your variance. Okay, how data points are say distributed around the min points, right? If you take square of that, that is nothing but the variance, right? The min of those sum of square error is the variance. So if you see here, so principal component is nothing but the vector that has the maximum variance. Okay, so that is what the and that corresponds to eigenvalue, right? If you remember eigenvalue and eigenvectors, so that is what we are looking at. Okay, so this is what the principal component. So what is second principal component? So second principal component is the projection where say that is perpendicular to this first principal component. Okay, and that you will see that this is nothing but the say second eigenvector of the covariance matrix and so on. Okay. So likewise, if you have if your number of features is k, you may have up to k number of principal components, first, second, third, and so on. So my example is only two-dimensional, so I have only one first component and second component. But if you have k number of features, you may have up to k number of principal component depending on the rank of your matrix. So if your rank is k, you're going to get k number of principal components. So this is what the say components of your data sets. Okay. So what is the third principal component? Third principal component is again vector perpendicular to say first and second and so on, right? So so that is how your say principal component will be Okay, so now, okay, so this is what we are looking at. So now, once you have the principal component, if you look at this diagram, so this, this projection, these blue lines are your original, say, x-axis and y-axis, the feature space. Now, once you find this principal component, what are you going to do? You are going to project your original data points along this principal component. Okay. So now, say if you see these left-hand side rectangles, so you have the first one is nothing but your original data sets. Second one, if you see your x-axis become now first principal component, y-axis now become second principal component. And what are these points? These are nothing but the projection on these components. So your data points now will be represented in the, say, space of these principal components. Okay, this is what we are looking at in the principal component analysis. And how do you, okay, so this, so for, if your data set is having something like n number of samples and d number of features, and so after doing min adjusted, and if you find the principal components, you are going to, you can have up to d number of principal components. So this is how the projection is going to be. But what is the dimension reduction here? I don't want to say consider all the components. Instead, I want to consider only few of the principal components. Okay, that is what. So instead of considering all the components, I'm only going to consider only up to k number of components. Okay, that is for, and I'm going to ignore say other components. Okay, so if you remember the say eigenvalues and the significance of eigenvectors, so you know that only say few of the principal component will be capturing maximum of the informations. So ignoring the, say, lower component does not really affect on the say information present in the data set, right? So dimension reduction here is nothing but you find the components and select only the top few principal components. Okay, so that is what the dimension reductions. So if you look at, see here, now I have reduced to k number of components. So the data set, the first row, which is nothing but a vector with d dimensions, it is represented by the first row of this in the component space, that is a vector with say k number of dimensions. This is what. Okay. So you just imagine now this data set is nothing but your text corpus, where your rows are the your this one documents, and the columns are the say features, unique words. So now your document the document vector is now reduced to from d-dimensional space to k-dimensional space. Okay, so this is how I represent a document in the say component space, and this is nothing but the embedding of the document. So if I want to find the word embedding, so represent the column, so I can do, instead of working in the term space, I can work in the say document space and do the principal component analysis and reduce the dimension. Okay. So now this is how say PCA works. Okay, so this is what the principal component analysis, and you can see that this principal component analysis is nothing but so just to give a brief about the theoretical background. Maybe I may need to skip this quickly, but just to touch upon that. So given this data sets, let us say I have a vector V, and so if I want to project on this V, I say we do D and the V. This is what you have seen, right? And I am looking for the V that has the maximum variance. That is nothing but the component. So V is the principal component. It has the maximum variance. So this one, if you see here, this variance of this D and V, you can see that this is nothing but the product of V transpose into S and the V, where S is the covariance matrix of the say matrix D. Okay, so you can see that from this easily you can see that. Okay. So you can see variance of V and the D, product of this projection, that is D and the V. This is nothing but the product of the principal vector that you are projecting and the covariance matrix of the data set and V. Okay, so this is what this one. So if I want to, so it tells you that now. So if you apply this, if you find the eigenvectors of the covariance matrix, that is going to be same as your principal components. Okay, so that you can easily see from some mathematical background. So that I am going to say ignore skip that, but just to give a quick information. So now I want to find, say I want to maximize this variance with a constant that V to V transpose should be a unit vector. So if you do the optimization on that using Lagrange multiplier, which that you know that you need to do partial derivatives with respect to V, then you are going to get this equation as V is equal to lambda V, and this is nothing but the eigenvalue eigenvector expression where V is the eigenvector, right? So this shows that, okay, the vector that we are looking at is nothing but the eigenvectors of the covariance matrix. Okay, so what is the PC? So okay, this is what the principal component. Okay, so I'll skip this. So what is the summary of this PCA? So given the data set D, you find the covariance matrix of this D, and then you estimate the eigenvectors of S, then select the K principal eigenvectors and represent the say data samples by this say K principal eigenvector. That is nothing but the projection on this eigenvector. So this is about PCA, and this is how in earlier methods people use to generate the embedding. Okay, and this is also very good method. So next, quickly I'll explain about SBD. So if you in the PCA, what we have seen how to find the component, and so in other way, this PCA is also kind of matrix factorization method. That is what I'm going to show. So as you know that there are various matrix factorization methods. Matrix factorization means a given matrix is decomposed into a product of say two or more number of matrices, right? So like LU, then QR, EBD, SBD, and so on. Okay. So eigenvalue decomposition and singular value decompositions are, I think, two of the popular, say, earlier popular methods. Okay, so that is, I'm going to briefly explain what is eigenvalue decomposition, singular value decomposition. So what is eigenvalue decomposition? Just to give a notion, eigenvalue decomposition is nothing but you are assuming that you have a say square matrix. The matrix A is a square matrix. Let us say this is order of n by n. Okay. So then let us say V1, V2, and so on up to Vn are the eigenvectors of this matrix A. In such that the lambda 1 is the, say, eigenvalues of eigenvector V1, lambda 2 is the eigenvalues of the eigenvector V2, and so on. And the I'll say lambda 1 is larger than lambda 2, lambda 2 is larger than lambda 3, and so on. So this is how we are arranging. Okay. So and you know that if you have a square matrix of order n by n, you may have up to n number of eigenvalues, right? Depending on the rank of the matrix. So if you have your rank of the matrix is n, then you're going to have n number of eigenvalues, right? So this in the form of eigenvector expression, I can write as A into V is equal to lambda V, right? So then this is nothing but A V1 is equal to lambda 1, V1, A V2 is lambda 2, V2, and so on. I can define, if you have n number of eigenvalues, I can probably write in this manner. V1 with this multiplication in the right-hand side. And if you combine them in the matrix form, so this rectangular representation is what you can see. So I can join all these n number of expression in some matrix where V is equal to V delta, and delta is the diagonal matrix where diagonal elements are the lambda 1, lambda 2, and lambda n, and so on, right? And A is the original square matrix, and the V, what is V? The column of this V, column vector of this V are the eigenvectors. So first column is the eigenvector of lambda 1, second column vector of V is the eigenvector of lambda 2, and so on. So you have n by n another V. So I can represent this this n number of expression together using a matrix. AV is equal to V delta, right? So now this V delta now, if I can write A is equal to V delta V inverse. Okay, this is what a decomposition. So A is equal to V delta V inverse is this decomposition is known as the eigenvalue decomposition. Okay, so now this is what the eigenvalue decompositions. So now if you look at some of the properties, so you may have inverse of V. For some inverse, you may not have inverse also. Okay? So, but for some, say, matrix, you may have inverse. But if you ensure that A is having n number of linearly independent eigenvectors, so A can always be decomposed. Okay, then that means, so if this property is satisfied, you will always be able to find the decompositions. Similarly, if A is positive semi-definite means A is equal to, for A, you may have some other, certain matrix X, and satisfying that X and X transpose is equal to A, then this A matrix is said to be positive semi-definite. And so if your matrix A is positive semi-definite, then you can also see that A is also symmetric because A is equal to X transpose, right? So if you have a symmetric matrix, eigen decomposition of A always exists. Okay, it not only exists, it also, you can also see that these eigen vectors are also orthogonal. Eigenvalues always greater than equal to 0, and say eigenvectors are composed of real number and so on. Okay. So since eigenvectors are orthogonal, so V inverse is equal to V transpose. So if your matrix A is a semi-definite, positive semi-definite matrix, you can always decompose A into a V delta V transpose. Okay, so this is what the decomposition. This is what the eigenvalue decompositions. Okay, if your A is say positive semi-definite. So this, like this, you can transpose if you have a square matrix. So then, what is the, if you look at here, what is the relation of this with the PCA? So you can map this to PCA because if your data set is M, okay, and you take the A is the covariance of D, and on A you apply the EBD. Okay, so if you apply EBD on A, then what you're going to have is, say this V will be the principal components. V1 is first principal component, V2 is second principal component, and so on. So this is what the decomposition. Okay. Then what is dimension reduction? Dimension reduction is nothing but you just ignore the lower eigenvalues, assign all to 0, and only you keep only the few, say k number of principal eigenvalues, and rest you assign to 0. Okay. So when you assign to 0, it is like you are reducing you are only considering the k number of principal components. So you get the covariance matrix, apply EBD, and select the say k number of components. Okay, then do the projections. Okay, so PCA can also be realized as EBD. So now, suppose, okay, this I will skip. But what? So in the eigenvalue decomposition, what is your assumption? Assumption is that your matrix that you want to decompose, A should be a square matrix, right? But in many of the cases, your A may not be a square matrix. It may be rectangular matrix. Suppose your data set is the rectangular matrix, right? So if you have a rectangular matrix, okay, then you have to apply the singular value decomposition. In the PCA, even if your data set is rectangular, you are converting to a square matrix, that is the covariance. Then on the covariance matrix, you are applying the, say, EBD. Okay. So, but if I want to apply directly on the data set itself, which is rectangular in nature, then singular value decomposition I can do. Okay. So singular value decomposition is applicable to rectangular matrix. So you have m by n, and just like your eigenvalue expressions, eigenvector expression, singular value expression is something like this: AV is equal to say sigma u, where sigma is called, just like your lambda was eigenvalues, sigma is called singular values. U is the left singular vector, and v is the right singular vector. Okay. So just like your number of say eigenvectors, if you have, depending on the rank of the matrix A, okay, you may have say something like if rank is r number of singular values and so on. So now, so if you have, so you can represent in this form, then you can now summarize these two, say some in the matrix form, A, B, U, sigma. Okay, then I can write A is equal to U sigma V transpose. Okay, so this A is equal to U sigma V transpose is what we call as the singular value decomposition. The singular value decomposition is nothing but A rectangular matrix is decomposed into U matrix, sigma matrix, and the V transpose. So what are these U, sigma, and V transpose? So the sigma is, again, just like your delta. Sigma matrix is not also a say diagonal matrix where diagonal elements are the singular values. Okay, so largest singular value is the sigma 1, next largest is the sigma 2, and so on. And what is U? Okay, U is the column vector of U is nothing but the eigenvector of A transpose. Okay, likewise, the row vector, the column vector of B, okay, are the eigenvector of A transpose A. Okay, and what is this sigma? Sigma, okay, are the square root of the eigenvalues of A transpose, A transpose or A transpose A. Okay, so A transpose or A transpose A will have the same eigenvalues, okay, but they will have different eigenvectors. Okay, so U is nothing but the columns of U is nothing but eigenvectors of A transpose, and the column vector of B is nothing but eigenvectors of A transpose A. This is what the singular value decomposition. Okay, so singular value decompositions, singular vectors and eigenvector have a very close relation that you can see. A transpose A can be defined, simplified in this manner, which gives you something like U sigma square U transpose. Okay, that is why we are telling that U is nothing but the eigen. So if you look at this, this is nothing but the EBD decomposition of A transpose. Okay, because A transpose will now be a square matrix and it will also be symmetric matrix. So now U, okay, U, the column of U, columns of U are the eigenvectors of A transpose, and the column vectors of B are the eigenvectors of A transpose, and you can see that eigenvectors are same. Okay, so say square root of singular value is going to be so singular value is nothing but a square root of the eigenvectors or eigenvalues of A transpose A or A transpose. So this is what the singular value decomposition. So now how do you reduce dimension over the singular value decomposition? So given a data set, now you decompose into U sigma V transpose, then you just, so if you, then what, I will skip this part. Then this, just like in the EBD, you remove the assign 0 to lower singular values, you only keep the top k number of singular values, and this is equivalent to reducing dimension. Okay, so now your A is decomposed to U prime, sigma prime, and the V prime, where U prime is nothing but U minus the say lower eigenvectors. Likewise, V prime is nothing but V minus lower eigenvectors. So now, so this is how, now if you see here, the rows of A is similar, is like it can be represented by rows in U prime. Likewise, the column of this A prime can be represented by say columns of V prime. Okay? Likewise, I can also realize. Okay, but what is the formal projections using the singular value decompositions? Given a matrix, given a new data D, okay, you perform say product of the data, the sample vectors, V prime and sigma prime. So this is what I'm writing the red color below. This is how I can project from say high dimensional space to low dimensional space. So this projection now after dimension reduction is called what we call as the LSI, latent semantic indexing, or latent semantic analysis. So latent semantic analysis, this decomposition is one such first method that has been applied in search engine to address say problem of synonymy, polysemy, and so on. Like say when I do a query, so if I do only the direct keyword matching, I will be only finding those results that match with the exactly match with the query, but other document related to the query, but do not have those keywords, that cannot be found out. So by using SVD or say latent semantic indexing, that is, so we also see that this can also capture the say synonymy relation in the text and so on. Okay. So this is again, this is the word embed. Now this can also be considered as the word embedding. Okay, so the document embedding in this space. Okay, so these are the two methods that has been effectively used say prior to this word embedding. Okay. But problem with this method is that this is not scalable. Okay, because you have to perform all this decomposition and so on. If you want to apply this on huge text corpus, it is going to be very, very expensive operation. So this is not scalable. So that's why this word embedding, word to back and so on, they are kind of dominating it. Okay, but if you look at some of the domain, very specific areas, something like all these NLP applications on low resource. Let us say I'm staying in Assam and we don't have much resource, textual resource in Assam is in the digital form. So then if I want to apply this neural based, deep learning based, you may not be able to get very good representation because you need a huge document collection for neural models, right? So then for this kind of low resource, say, area, these matrix factorization based methods are still important. Okay? So you can see even today, if you look at something like cross-lingual embedding in low resource area, many of the recent studies will be based on these matrix factorization based methods. So you have issue with these methods, though they are effective, because these methods are not scalable. Okay, so that is how say it moves to neural based methods. Okay. So the methods of word to back, has it been discussed in the first session?
Yes, it was discussed up to some extent actually.
Okay, so should I briefly touch upon it?
Yeah, it has to be, I think.
So okay, so let us see what is word to back. Okay, so again, for understanding word to back, you need to understand briefly, say some basic understanding of the neural network, especially multi-layer perceptron. So I think yesterday you have discussed about different neural models. So I hope you already say familiar with these models. But let me just quickly touch upon uh, this model. Okay. So in the word to back, as you know that the neural model that you're going to use is nothing but the multi-layer perceptron. Okay. So in the multi-layer perceptron, as you know that you have something called input layer and you have something called output layer, and you may have any number of say hidden layer in between. Okay. So in this diagram, I have the input layer, then one hidden layer, and the one output layer, and these nodes are completely connected. Okay, all nodes in one node in say input layer is connected with all other nodes in the hidden layer. Likewise, one node in hidden layer is connected with all other nodes in the output layer. Okay, so this is called densely connected network. Okay, so let us assume that this is a densely connected network, and I have one input layer, one output layer, and one hidden layer. Okay. So so this is the visual visualization of this network. Okay, then in the input layer, what are you going to take? So I am going to take a vector. Okay, so the connections in input layer x1, x2, x3. So if I have 3 nodes in the input layer, that means my input vector is going to have 3 elements. The dimension of the vector is going to be 3. Likewise, if I have 2 nodes in the output layer, that means my neural network is going to give me a vector of dimension 2. Okay, so the number of nodes in each layer represents a vector of that particular size. Okay. So if I have a multi-layer perceptron of this structure, that basically means this model or this network is going to take a vector as the input, and dimension of the vector is nothing but the number of nodes in the input layer, and it is going to produce another vector from these models, and the dimension of this vector is going to be 2 in number of nodes in this layer. And every connection between one node to another node will have some associated weights. So if you see here, W11 is nothing but weight associated with the connection between first node in the input layer to first node in the hidden layer, and so on. Likewise, connection between the hidden layer and output layer. So if you see this, you have 2 types of weights. One set of weights between input layers and the hidden layer, another set of weights between hidden layer and the output layer. Okay. So what is inside this node? Inside this node, you have 2 components. So one component is called perceptron. What is this perceptron? Perceptron is nothing but the weighted summation of, say, the input vector. So this diagram, if you look at the right-hand side diagram, so perceptron part is nothing but the product of, say, you are multiplying the x1 with the W11, right? And x2 with W12. X3 with W31, X2 with say W21, and so on. So sum of this, okay, this is what the perceptron is. Okay. Then this perceptron is again passed to some regularizer, something called activation function. So activation function try to regularize the output from some output within a range like 0 to 1 or -1 to 1, and so on. Okay. So you are going to have 2 functions inside each of this node. One is the perceptron, another is the activation function. So output of the activation function is what you're going to have as the output from the node that you note here. Okay, so this is activation function, and there are different types of activation functions. So this is some of the activation functions, like and some of the most commonly used activation functions are like sigmoid, then say hyperbolic tangent, LRU, say RLU, and so on. Okay, RLU. So these are some of the commonly used activation functions. Okay. So now, again, so you know that you have forward pass and the back propagation in the neural models. So what do you mean by forward pass? Forward pass is that you just assume that you already have the weights, connecting weights. You already have some weights in these connections. Okay. Then forward pass is nothing but if you give a vector in the input, what you will be getting in the what vector you will be getting in the output layer. So this journey, this propagation is known as the forward pass. Okay, so that is nothing but if you just try to see from here, you give a vector in the input layer, then so this is then from the input layer. You apply this perceptron activation function in the hidden layer, and go to the produce the output vector from the hidden layer, then again pass to the next layer, and applying the same methods like perceptron and activation function in the output layers. Likewise, you move, like say from here you move to this, from here you get the hidden layer output, then again apply the hidden layer output to the say next layer, and so on. Okay? So this movement is called forward pass. Okay? So if you look at this process, you can you see that the weights between input layer and the hidden layer. Okay, so how many weights you have here? You have, so for every node in the hidden layer, you have something like that many number of connections, equal to the number of nodes in the hidden layer, right? So you can see that this is nothing but a matrix. Okay, so the connection, the weights between input layer and hidden layer can be visualized by a matrix W. Okay, so where the row of the W is nothing but each row represents the nodes in the input layer, each column represents the nodes in the hidden layer. Okay, so I1 and S1 is nothing but W11. I1, S2 is nothing but say W12, and so on. You can visualize this as the you can see this as a matrix. Likewise, connection between hidden layer to output layer is also another matrix B, where each row represents the node in the hidden layer, and each column represents the node in the output layer. Okay, so this is the matrix. Okay, and those propagation that we are talking about, that is nothing but the product of the vector and these matrices. So if you see here, what is H1? H1 is nothing but the product between the input vector 1, 0, 1. Okay, input vector this X with the the connecting weight towards the hidden nodes. Okay, so this is nothing. So this is the product. So each element, if you see H1 is nothing but product of this. H1 is, so first you find the perceptron, which is nothing but the W1 product of the X1 and W11, X2, W21, and so on. So this is nothing but, this P1 is nothing but product between the input vector X and the column vector of W. The first column corresponds to the first nodes in the hidden layer. So this product is what the P1. Then you apply to some activation function. In this example, I have given sigmoid functions. Then H1, this H1 is the output from the first node in the hidden layer. So what I'm trying to say, likewise you can keep moving this, right? So what I'm trying to say here, so the forward pass I was talking, the pictorial representation, that is nothing but the product between the input vector and the matrix W. So if I perform dot product between X transpose into W, I'm going to get P transpose. Okay, So I'm using transpose because I have represented as a row vector here. Okay, so if you are using column vector, then it is going to be something like W transpose X and so on. So ultimately, everything is nothing but your matrix algebra. Okay, product between everything is product between matrix and a vector. Okay, this is what you are getting in the the output from hidden layer. Likewise, in the next layer also the same thing. Okay, the output from this output layer. Okay, this is nothing but the product of the output from hidden layer into the matrix V. Okay, then apply the activation function that whatever you need. So this is what this is also. So forward pass is nothing but the sequence of this matrix multiplication, vector and a matrix multiplication. So this is what the forward pass. So now I can summarize all this process into the output from this neural network is nothing but sigmoid to the input vector and W. Then on the output of that you apply again product to the V matrix and so on. Okay, this is what the forward pass. Okay, so this is how it is going to move. Okay. So now, so when you talk about a model, a parametric model, so what are the parameters of this neural network? Okay. So what is known and what is not known? So if I have a training examples and I'm trying to do some classic supervised models, I know what is X, I know what is Y, and what I do not know is the matrix W and the matrix V, right? These are the unknown matrices and these are the parameters. Okay, but I need to for forward pass, I need to have these values, right? So the parameters of these models are nothing but the matrix W and the matrix V, and in any neural models, what we're going to do is learning this vector. Learning these matrices, matrix W and the matrix V. You need to learn from the training examples. So what do you mean by learning? Okay, so in neural network, it is the process of learning is something like gradient descent. That means you start from some number, random number, then slowly move to move to the actual values. Okay, using some error adjustment. Okay, this is called gradient descent. Okay, so what is that? So let us assume I'm just trying to explain that error by using these examples. So let us assume that given this example, so let us assume that I have some initial weights, initial values of some W and V. Okay, so these are some initial weights. Now, if I apply my input vector, I have got some output vector that is nothing but the observed vector that I'm showing. Okay, then but since I have my training data sets, I know what is the actual values that you should get. That is nothing but the expected value. Okay, then if in observed value and expected values are same or very close, then I can say that the weights that you have are correct, right? If they are not same, then this you are getting different results because your weights are different. Weights are not correct, right? So then it is an error. So now, so if you have for a given W and a V, if you have some error, okay, then you have to do the correction. So what is that error? So in the any learning model, you will have something known as the loss function. Okay, loss function. There may be various loss function, but just for this demo, I am just telling that okay, my loss function is nothing but difference between the observed and expected, and perform something like Euclidean norms or something. Okay, you perform some norms or something like square of this difference, whatever. So I can apply some loss function here. So my E is my error. Okay, so if I have an error, so how do I do the correction? So you already know that in the optimization theory, if you have a function and if I want to maximize or minimize, what you do the partial derivatives with respect to the error functions, right? And then if you have a constraint, you put a constraint. Otherwise, if you have a constant, you perform the constant optimization with Lagrange multiplier or something. Otherwise, you take the partial derivatives and assign to 0 and estimate the parameters. Okay, that is what I'm going to do. So my error function is E, okay, which is defined as something like this. Now, and what are my parameters? My parameters are all the elements in V, right? So I have to take partial derivatives of this E with respect to all the elements in this V matrix. That means with respect to every connection that you have in this layer, you have to take partial derivatives. So that I have just represented by partial derivatives of V. So partial derivatives of V is nothing but I'm telling you take partial derivative with respect to every element in the matrix. Okay. So that is what in the next line I'm showing. Error of say delta ij. Okay, this is the error that you are looking at, the adjustment error, the gradient error. Okay, for the connection I and j. Okay, so now you're taking E derivatives of E with respect to Vij and assign to 0, and that will, so then you can estimate from here, you can estimate the value of Vij. Okay, so then once you get this say gradient, this one, then now you previous values of say values of V will be updated. Okay, so the new values of Vij will be all value of Vij plus the delta ij. Okay, then you, so then your delta, will you directly use the entire say delta or say some fraction of this? Okay, then you can decide. So so this mu is known as the error rate. If you have a very small error rate, that means your gradient will be moving very slowly, and you will not be missing local minima or local maxima, whatever you're looking at. But your eta value is very large, then you are quickly moving, and then you may be missing the actual local minima or local maxima. Okay, so mu is also some hyperparameter that you need to provide. Okay, user need to provide. So this is how you're going to learn, say, new weights of, say, these B matrices, and this is what we call as the backpropagation. Okay. So likewise, for learning for the, say, W matrix, you perform partial derivatives of E with respect to W and do the, say, find the new values of W. Okay. So this is, so likewise, you keep repeating this, okay, keep repeating this for till you find till your error is acceptable or 0. That is what the convergence point. Okay, so that is, so once you converse, your model converse, then you have found the appropriate the W parameters and the V parameters. Okay, so this is what the, say, multi-layer perceptron and how you do the forward pass and the back propagations. And what interesting thing for this model is that you can use this model for various tasks, classification tasks, regression tasks, probability estimates, representation learning, and so on. So for various tasks, you can use this model. Okay. So in the word2vec, you are going to use this model for probability estimates and representation. Okay, that is what this one. So just to explain how to use this model for probability estimates, let me give one simple examples. Let us assume that I have a sentence, say the man sat on the floor. Okay, so, maybe one popular examples like the cat sat on the floor and so on. So we have I have that sense to man sat on the floor and something. Then let us assume that I am creating a training example to create the probability. Okay, something like the bigram pairs, the main set on the, and so on. I have created these pairs, collection of pairs from your training text corpus. Okay, so I have a collection of these pairs now, subsequent words. Okay, then I want to estimate what is the probability that if I give the, I should be getting men. This is what I want to estimate. Okay. So how do I do that? So if I want to do that, say a little modification on my multi-layer perceptron, what I'm doing is now I have, if you have n number of say words in your corpus, if you have n number of words in the corpus, I'm having n number of nodes in my input layer. Likewise, I'm having n number of nodes in my output layer. Okay, that means every nodes in the input layer represent one word in my corpus. Likewise, every nodes in the output layer represent one word in my corpus. Okay, so if I want to find this probability, the idea is like, suppose now x1 represent one word, and something like O1 O2 represent another words. So if I want to find probability of getting O2 given I1, then what I will do, I will give say one. I will activate the say node I1 and try to see, am I getting the maximum values in the O2 and so on. Okay, so this is how I'm going to set up. Okay, so for doing that, so we use some form of encoding that we call as the one-hot encoding. One-hot encoding means in this vector only one element is 1 and the rest are 0. Okay, so if I want to give some words, say represented by index I, only that index will be 1, rest will be 0. Okay, so if I give one-hot encoding as the input, I am expecting another one-hot encoding as the output. So where the index where the output become 1, that is what the prediction. Okay, so in this example, I am predicting. So my model is trying to do something like the probability of getting the word y2 given the word x1. That is what I'm expecting. So if you assume that x1 represents the word the and y2 represents the word men, then this is nothing but probability of getting men given the word the. Okay, so this is how I'm going to set up my experiment. Okay, so this okay, so this is the first. This is the basic idea in word to back. Okay, so what is word to back? Let us just see the experimental setup. The objective of the word to back is to predict the target words given the words in context. Okay, this is one of the objective. Okay, so like say, oh, so what is this target? What do you mean by this context? So if I consider a sentence like the man sat on the floor, let us say if I say that my target word is men, okay, and the context words are something like the words around this neighbor, say around these target words. Okay, so if I say I'm looking for window size of 2, then my context for the target word men are the set and on, because my window size is 2, so I will look 2 words say preceding the target words and the say after the target words. Okay, so likewise, so if I consider the target as the main and the window size as the window size is 2, then context are the set on, and from this I can generate the training samples, the main set, main on, and so on. Okay, so for a given text corpus, okay, let us say you have a text corpus, you generate all these pairs of words considering each word as the target and the context around that. So for this simple examples, if the become the target, so and window size is 2, then I will be having training samples like the main, the set, and so on. This pair will be generated. Likewise, if main is the target, then I will have main, the main, set, main, on, and so on. If set is the target, then I will have set, the set, main, set, on, and so on. Likewise, from all the sentences in the training corpus, you generate these pairs. Okay, these pairs of words. Okay. So in word2vec, there are two basic models. One is called continuous back of word and skip gram. So continuous back of word is something like, given the context, you try to target the target. You try to predict the target. Okay, but whereas in the skip gram, given the target, you try to predict the context. So that is the say SIBO and skip gram. So only difference is you're going to use the same neural models, but only difference is how do you set up your experiment. Okay, in the SIBO, you given the context, you try to predict the target, and in the skip gram, given the target, you try to predict the context. Professor Vishwanath, how much time I have?
Professor Ranveer, I think you have some 2 or 3 minutes only.
Oh, okay, let me type it quickly. So this is the only difference between SIBO and skip gram. So, but neural models is going to be same. Okay, so I think I will skip this neural part. Okay. So what is the what I'm going to discuss is, given the context, predict the target. Okay. Let us say I'm given the context like main and the on, try to predict the word set. Okay, this is what I want to have. So this is the same neural model that we have discussed in my these examples. This model is what is used. Okay. So but interesting thing here is that the activation function in all these nodes are linear. Okay? So only the linear activation functions are used. Other are same. Okay. So now, if I give, so now, so in the input layer, I'm having two branches. Please ignore one of the branches. Let us say you are ignoring the lower branch. I'm only considering the upper branch, that is the main. Okay. So this is like, given main, what is the probability of getting set? Okay. So when I give main, so I'm giving the one hot encoding. You see here, I have only in one index, rest are 0. So it means that this red one is the say node corresponding to the word main. Okay. And in the output also, I am expecting to generate one hot encoding where red corresponds, the one corresponds to the word set and rest are 0. So this is what I'm giving. So if I give this neural models, okay, so you do this training, training for entire word pair that you have created from your data sets. You give one pair and then do the back propagation, another pair and back propagation and so on. Okay, but especially in SIBO, what they do is they try to give the context, all the context words together, and in the hidden layer they try to create some average of it. Okay, but it depends on how do you train. Okay, so in some model you don't strictly do this way, but in some model, instead of say doing in the arbitrary sequence, they try to do together and take average of it, something like that. So now you do this forward and back propagation, forward back propagation for all the training pairs. At the end of it, it is converse. Okay, let me skip this part. Okay. At the end of it, it is converse. Okay, it converts to some vector W and the vector V. Okay, so let us assume that it is converts to the vector W. Okay, the one that I'm showing in this figure. So what is this W? If you look at here, is say this is W transpose. That means each column corresponds to corresponds to each node connection from one node in the input layer to the rest. Okay. So what is the size of this W? The size of this W is something like n by d, where n is the number of nodes in the input layer and d is the number of nodes in the hidden layer. Okay. So that basically means I want to say learn the matrix W and the matrix B, and the size of matrix W is n by k, right? Where so now in the what to back. So suppose if I want to generate an embedding of size 100, for example, then the number of nodes in the hidden layer is going to be 100. So if I set 100 in the 100 number of nodes in the hidden layer, then I'm going to generate a matrix of size n by 100, right? And each row of this W will have a row vector of size 100. Okay, that is the embedding of the of each words, because each row corresponds to each word in the corpus, and each word is represented by a vector vector of dimension 100, where 100 is the number of nodes in the layer. Okay. Likewise, what is B? B is also a matrix where you have 100 by n, right? So each column of this B is defined by each column is column vector is nothing but the is having dimension 100. Okay. So what embedding is nothing but using SIBO is nothing but after doing this training for entire training data sets, what are the vectors, what are the matrix W and the matrix B. Okay, so if I'm any one of these logically, any one of these say matrices you can consider. So if you are considering W as the say embedding matrix, then each row of this matrix will give you the embedding of each words defined in the associated in the input matrix. Okay, so that is what the word embedding. Okay, so this is how you generate the word embedding. So I am skipping this. So okay, yeah. So now this is what embedding, that how you get using the SIBO, but there are some issues in this learning, because the number of pair is very large. Okay, so the number of back propagation that you need to do will be extremely large, like this partial derivatives that you are doing. So to reduce that, they use something called negative sampling. Negative sampling is like, instead of doing back propagation for all the output nodes, you only do back propagation for the target node that you are looking at, and some of the other say 0 nodes in the output layer. Okay, only few of them you do, and that is what the negative sampling in the very high level understanding. And they have seen that with around 5 number of negative sampling, 5 nodes, they are able to get a reasonably good results and so on. Okay. So that is what the what embedding. So just let me spend about 1 minute to just talk about the applications. Okay. So now this is just to illustrate what is the output of this word embedding. So if you try to plot the similarity, try to project this embedding into 2-dimensional space using PCA or TSNA, some other projection methods, you found that many of these words are quite similar. Okay. Then I have one small demo for to show this. So what I'm doing here is I'm providing, so luckily Google has provided word embedding of huge corpus, news corpus. So I'm directly using that embedding given by the Google News. Okay, so the link that the file that I'm using here, Google News vector, this is the embedding provided by the Google. Okay, so I just want to show you that show you that you will be getting say very interesting results. So one thing, if you see the last results, if you give the nice as a word, and I want to find what are the topmost similar word to nice. Okay, so using the vector similarity, cosine similarity, it is giving something like good, lovely, and so on. So this is interesting, right? So you have without any prior information, just by seeing the huge corpus, users run these very simple models, and you are giving embedding, of dimension 300, and that it is giving, and it is going to give, is able to give these quite similar, semantically similar words. Okay. Likewise, since it is a vector, so you can also do some vector arithmetics, right? So if you perform something like women plus king minus men, then it is giving something like queen. Okay, like man plus king minus queen, it is giving something like boy and so on. Okay. So it shows that this simple model is able to capture say semantic relations uh, and provide the corresponding embedding. Okay. So how do you apply this embedding on say various NLP applications? So if you look at something like very simple like classification models like sentiment analysis, okay, then given a particular sentence, I want to say whether it is positive or negative or something, some classification task. And let us say you are using say multi-layer perceptron for the classification, because the way you are using this embedding will also depend on the underlying say classification model. So you have just seen multi-layer perceptron. So let us say I'm going to use multi-layer perceptron for say this classification task. Then one very simple model might be, if I have something like a sentence, you try to find from the word embedding, you try to find a sentence embedding. So which can be something like linear summation of what is summation of all the words in the say a sentence, and the resultant vector you give to your multi-layer perceptron and build a classifier. Likewise, if you have something like LSTM kind of models, then you don't have to do this sentence level embedding. You can directly give the sequence of words in the present in the sentence. So this word embedding you can directly give. Or say if you are looking at the convolutional neural network, then you can construct the matrix of representing the sentence, where say for every words you have one of the vectors and create the say matrix, and you apply say matrix to your convolutional neural network and so on. So before this word embedding, the same thing you can do with, as I said in the beginning, you can do with the traditional way of representations, but you say performance that you get with the embedding is much higher. So you can, but if you try to say which one is better between neural model and the matrix factorization based models, this I don't have the exact answer. But if you have the large, if you use a large corpus, neural model is fine. But in the smaller data sets, in many of the applications, traditional approaches are also giving better results. Okay. So I think since in the interest of the time, maybe I will stop here.
So thank you, Professor Tanasam Ranbir. And now for a couple of questions, maybe we can open this for the audience.
Yes, sir, no problem.
If there are any questions, quickly it can be asked, because we are already running late. So if there are no questions, then let me thank Professor Ranbir for technical explanation of word to vec and about SVD, PCA, and all these things. And tomorrow also we are having one more session from Professor Ranbir. So now for this session, let me thank Professor Ranbir. Thank you.
Thank you very much. So see you tomorrow. I'm signing out now.
Yes, please.